Queuing theory is the topic today. Why queuing theory? Well, in the context of complex systems, computer-based systems, queuing is happening everywhere. So queuing is essential to understand the behavior of and the performance of the systems that we are building or analyzing. Queuing theory is a topic of its own. An in-depth analysis of queuing systems is hard, and some of it is done, for example, in the course on stochastic processes by Olivier Lévesque. We will not go through that, but we will go through the general laws, and fortunately, the most important results are easy. So this is what we will cover in this course. But let's start with perhaps the simplest of all queuing analysis, which is about deterministic queuing. Deterministic queuing means we want to find bounds that are not probabilistic. Right? So it applies to worst case analysis. That's a hot topic today in the context of what is called time-sensitive networks, networks used for industrial applications, for running the control and command applications on vehicles, cars, automatic cars, planes, etc. It also applies, to, as we will see, to transient analysis. Classical queuing theory is concerned with stationary behavior of a queue, but sometimes we want to analyze what happens after a sudden arrival of a huge burst, for example. So to get the idea, let's study a simple example. The simple example is, how can we size a playback buffer? What is a playback buffer? Well, this is what you are using now when you listen to me with Zoom. The data that is sent by my computer is at a quasi-constant bit rate. The network imposes a variable delay, so the received bit rate is no longer constant. There is packets queuing in the network, and your player has to play the video and the audio at exactly the same rate as it was sent. In reality, modern codecs have a rate that is not constant, but to simplify the analysis here, I will assume it's constant. So how can you recreate the constant rate that was at the source at the destination, where the classical solution is the playback buffer? So you store the data in the buffer, you don't play them immediately, as shown here, and you play them from the buffer instead of playing them directly from the network. So you add an extra delay on purpose. Does it work, and how should the playback buffer parameters be computed? That's the question. To answer such a question, which is very typical of deterministic queuing, the main trick is to look at cumulative functions. What are the cumulative functions? Here I'm showing two, A and D, A as arrival and D as departure. Those are functions that count the number of bits that have been input to the system of interest between 0 and t. For example, that's the red curve here. And D is the same for the departure. That's the blue curve. If the system is lossless, then the red curve is always above the blue curve because the bits that go out must have come in. The only law of physics that we're 100% sure is causality. Things happen based on what happened in the past and not the other way around. So A is larger than or equal to D. And we can read in a very simple way the quantities of interest on this diagram. The vertical difference, A of t minus D of t at time t, is how many bits have come in minus how many have gone out. So this is the number of bits that are in transit in the system. If the system is a queue, that's the amount of data that is being queued. If the system is a more complex network of queues, like most realistic systems, it is simply the number of systems that are in transit. This is also called the backlog of the system. Similarly, if I plot a straight line from time t here, I go from time t, I go to the y-axis, and I plot a horizontal line starting from there, from the red curve until I reach the blue curve. Then what am I doing when I'm doing that? Well, if the system is FIFO, FIFO means it preserves the order of arrival of the bits. Most systems are FIFO per flow, not systems that we are interested in. Then this duration is, if we look at, since we are at the same horizontal, at the same height here, when we hit the blue curve, all the bits that have arrived at this time have gone out. So this time is exactly the time when the last bit that has arrived as time t is leaving. So this is the time spent in the system by a bit that arrives at time t. So the horizontal deviation gives us the delay of the system. The worst case delay would be where the deviation is largest. Similarly, the vertical deviation gives us the backlog. This is a bit hand waving, and we would need formulas for this, but we will not see them here. I will point to references where you can find them. Let's apply this simple method of analysis to our original playback buffer problem. So I'm showing back my system. I have A of t, which is the data that is sent by my computer, the network, and A prime of t is the data as it comes out of the network. So in this simplistic thing, I'm assuming I'm coding at a constant rate. So A of t is given, at least if we ignore the packetization effects, as a straight line here. So that's a fluid approximation of the reality. And now what comes out of the network is given by this curly line here, which is not a straight line. And we see that the horizontal deviation between the two is the delay. And the delay varies because there is queuing in the network, typically. Or other mechanisms like medium access control protocols, etc., reasons that cause packets to not have the same time. So we have the red curve here, and we want to recreate, if we want to play the audio and the video without any quality of service impairment, then we want to recreate exactly what was at the source, with a delay, of course. So we want to play the blue curve out here. So the classical approach, which is used by most systems, is to have a delay constant, delta, for which we wait to have a constant delay delta, for which we wait when the first bit or the first packet arrives. So at this time here, a packet arrives. I will not start playing the video immediately. I will wait for a duration delta here. And then I will continue to play for this time. Now, if delta is chosen in a way such that the delay variation is bounded by delta, plus or minus. Delay variation means the difference in delays between two packets. Here, I'm taking only since I fixed the delay at time 0, the delay variation between the first packet and any packet sent at time t. So this is also called delay jitter. If the delay jitter has a bound delta, then on this graph, we see what it means. It means that the d of t is bounded between d of 0 plus or minus delta. That means that if I draw a horizontal line from A of t with amplitude d of 0 minus delta, I obtain this red line here. And if I do plus delta, I will obtain this blue line here. So this jitter bound means that the curly red curve, the arrival curve at the exit of the network, must be between those two lines here. In particular, it is above the blue line, which means that if I play the data using the blue line, which means at a constant rate r, using this initial offset delta, the red will always be above the blue, which means that my system will be causal, or in other words, there will be no starvation. Whenever I have something to read, I can take it from the buffer. I will not have an empty buffer, in which case the blue line will have to wait, would be broken here. So this simple analysis gives us a first hint. How much should you wait before reading out your playback buffer? Well, you should wait for some quantity delta that is an upper bound on the delay jitter in the network here. So we have sorted out the size of the delay offset of the buffer. Now, we are probably interested also, in particular if we build this in hardware, in knowing what is the size of the buffer. How much data can there be in the worst case in this playback buffer? Here I'm proposing 4 solutions. Is any of those solutions the correct one? I close the poll in a few seconds. And the correct answer is the majority, 2R delta. Very easy to see. If we remember that the backlog bound, so the size of the buffer must be such that the backlog, the difference D A prime minus D must be less than or equal to the size of the the size of the buffer must be less than the worst case backlog here. Now the backlog, as we have seen a few minutes ago, is given by the vertical deviation between the input of the buffer, which is this red curve, A prime, and the output, which is D. Now we know that the red line is between the lines D1 and D2. Therefore, the worst case backlog is the vertical difference between those two lines. So the difference between the two lines is 2 delta, the slope is R, so that gives us 2R delta. Voila, so that was our first example of what is called deterministic queuing, also called network calculus. We see that the essential instrument is the use of those cumulative arrival functions. We can do a bit more. If you're interested, you can talk to Hossein, who is an expert in that field, and is doing a PhD on the application of deterministic network queuing analysis to time-sensitive and real-time networks. For the rest of this module, we will talk of the other aspects that are more stochastic. In particular, we will see what is called operational laws. There are a few laws. The most well-known and most useful one is called Little's law. So it's a bit like laws of physics that they apply to queuing systems, but as you will see in the quiz that I will ask you to do next week, you can apply it to lots of other systems in fields that are not necessarily strictly modeling of computer systems. The framework is the following. I assume I have a system in which there are entities that arrive. In the language of queuing, we would say jobs or customers arrive. And I call lambda the rate at which they arrive. The rate lambda means in average per minute or per second, there are lambda jobs or lambda customers that come into the system. Then those customers stay for a certain duration, and I call capital R the average duration. In queuing theory, R is called the response time, is the time between arriving to departing from the system, averaged over all customers here. So it is the time that you would, it's the average that you would get if you ask a number of customers chosen at random how much time they spent, and you do the average. And if you do that for 1 zillion customers, you will have this theoretical quantity R. So R is an average computed from the customer viewpoint. Now, N is another average, which is the average number of customers in the system. That's typically the operator of the system is interested, sees that number. It is how many are in the system here. And we can take an average. Now, what does this average mean? Here, it's a time average. Right? So if we sample the system randomly or every second, for example, we ask how many are there, and we do the average, the sum of all the numbers we've seen divided by the total duration of the interval over which we've averaged, we will obtain this quantity here. Then, under very general conditions, we have this relation. Lambda times R is equal to N. This relation is called Little's law. One way to remember it is to think of it as a call center. Imagine there's a call center where you call and you pay 1 franc per minute. Right? So as a customer, in average, R is how much you pay. Right? When a customer comes, in average, you stay R, so you pay R. The system, in average, receives some amount of money, which is given by the average number of customers in the system. If there are 20 customers in the system, they pay 20 francs per minute. So in average, if there are n customers in the system, I receive n franc per minute. Now the system is visited by lambda customers per minute. So the money that comes into my pocket as an operator of the system is the number of customers multiplied by how much time each of them pays. So I will receive lambda r franc per minute. I know that I receive also n franc per minute, so lambda r is equal to n, another way of seeing it. What we will do now is analyze when exactly this relation holds. So this relation is quite general, and to see why, we will analyze what we would do if we do a simulation. Now you know how to simulate a system, or by the end of this lab, you should be able to know that. So here I'm showing a queuing system and a sample path that we obtained, for example, for a simulation. So at time t1, a customer arrives. On the y-axis, I show the number of customers in the system. So it jumps from 1, etc. The system is FIFO, for example, in this case. So at time t2, one customer leaves. So R1, t2 minus t1, is the residence time of the first customer. And I call B of t the backlog, so the number of customers that are present in the system. Assume for such a system, you would like to compute R, the average response time, and N, the average number of customers in the system. How could you do this? Well, there are multiple ways of doing it, but one way to do it, a very classical way, is to use a counter that is incremented for each of those quantities of interest, to use a counter which is incremented at every change that happens in the simulation. This is what is called a discrete event simulation. Discrete event means there are discrete points in time where events occur and the state changes. Between events, nothing changes here. So for such a simulation, it's quite natural to update the counter when there are events. So here I use two counters, one that I call a response time counter, which is the counter I use to accumulate things, the numbers that at the end will give me the average response time. So this is the counter where I will accumulate all the time spent so far by all the customers who are in the system. And at the end of the simulation, I will divide this by the number of customers, NB cost, which is the total number of customers that have existed in my simulation. So this is how I will estimate R. Now, how will I estimate N? Well, I will also consider a backlog counter. The backlog counter takes the time integral of the quantity B of t here. So that is a continuous time integral, but of course, since the function B of t is piecewise constant, this is in fact a discrete sum here. So we'll do the same. The backlog counter at a given time t will accumulate will take the integral of the number of customers since the beginning of the simulation until now. And when I finish the simulation, I will take the value and divide it by capital T, where capital T is the duration of my simulation. So this is how I will obtain R and N. Incidentally, I can also compute my arrival rate, how many customers have arrived, by taking the total number of customers that I have seen in my simulation divided by the duration of my simulation. So this is how I would estimate lambda. I said that we can embed the counters in the simulation so that we can incrementally compute their values, and at the end we only need to do the division by T and NB customer, as opposed to other methods that would consist in replaying the simulation, recording all the simulation, and then observing all the arrivals and departures and counting the time spent here. That would be less efficient. So if we use this incremental approach, how is each counter updated? For example, at this time instant, T2, this time here, when there is the first departure of customer one. So imagine you have to write the code. Which of the lines of code would you take? I close the poll in a few seconds. Now we don't have very conclusive. If you had to take a decision on this, we would be embarrassed. So let's see the solution. Are we recording, Hossein? Thank you. Sorry for this divergence. So how do we update the counters? Well, since response time accumulates all response time spent so far, at time t2, when this event occurs here, at time t3, I assume I have done the accumulation correctly. So what I need to do is add to this counter the value that corresponds to the interval t3, t2 here. Since the response time accumulates all the response times, I need to add this interval, t2 minus t3, multiplied by how many customers have had such a response time. How many customers have had it? Well, it is the number that is given here. This is this number here, which is the number just before the departure of t2, just before time t2, or just after time t3. So this is how much the increment will give. Here in this example, there are four customers. BFT2 minus is 4. So each of those customers have spent that amount of time. The counter should be incremented by this. For the backlog counter, we need to add into the integral the value of the integral from t3 to t2 of bt, which is exactly the same here. It is the value 4 multiplied by the interval here. And this is the trick. The increment of those counters are the same. If they start with 0, which they will, then those counters, in fact, at every event, keep the same value. So at the end of the simulation, they have the same value. And since the response time is obtained by this formula, and the average number of customers by that formula, and the lambda, the arrival rate, by the ratio of the number of customers to the time, then by simple algebra, we see that lambda r is exactly equal to n. So that's a take-home message. When is Little's formula true? Well, if you count exactly in the way that I said, the answer is always. It's always true. I said if you count in the way that I said, because there are small variants that could occur on how you count. For example, I said here, if the simulation ends at some time t, so it ends and some customers might be in the middle of a service. So with the way I said here, the customers that are in the middle of the service, they are still accumulated in the counters. So if I count only customers that had a full service, I will have a slightly different thing. So this formula is exactly accurate if we count with the way that is given here, which is a natural way of counting. Other ways of counting might give slightly different things. Also, in fact, Little's formula, if you look up on Wikipedia or in the internet, is given usually in the context of stochastic systems. So if I have a queue that is a stochastic system, those quantities that I'm doing here are estimates of a theoretical quantity. For example, lambda, the arrival rate. If I say I have a Poisson process as arrival of rate lambda, if I count the number of customers that arrive over a duration t and I divide by t, I will find not exactly lambda. In fact, that's a way to estimate the parameter, but we will have it with a confidence interval around it. So if we talk of the theoretical value for a stochastic model of a queuing systems, those things are approximations, but the formula is also true. So the Little's formula is also true, not just for a simulation, but also a stochastic model, provided, of course, that it is a stable one. So provided that there's a stationary regime and where we replace these averages that I said by expectations. And then what happens when I have a stochastic system? If t is very large and the number of customers is very large, then those little differences that I mentioned in the way of counting, they vanish in front of the main quantities. So they go to 0 when capital T goes to infinity. So take home message, Little's formula is true in practice for any system, but also in theory for any stochastic model as long as it has a stationary regime. If you look up on publication, most of the time we find only the second case. And a few years ago, in the version of queuing, we asked the students in this course to simulate a queuing system and to verify Little's formula. And I was expecting to find that Little's formula would be only approximately true when the simulation runs were very short, and some of your colleagues did 2 short simulations, where I was expecting that they see that the formula doesn't work. And to my surprise, I found that it worked. And I did a bit more research, and I found that there is an explanation that is that it works always in all systems when we count in the correct way. Voila. So Little's formula, I can only stress it again and again. That's probably, if there's one formula from queuing theory we should remember, that's this one. This will be quite useful in a number of analyses. Here's an application, in fact, of Little's formula. It's called the Utilization Law. So consider, for example, here a single server queue. So a single server queue means there is a queue, jobs arrive, they are queued, and the job that's at the head of the queue or whatever other queue management system there is, one job is selected when the queue is idle, the customer is served, then it leaves, and then the next in the queue is goes into service. If the queue is empty when the customer leaves, then the server remains idle until another customer arrives. So this is the single server queue. It's a generic model. There are many variants of the single server queue. Variants have to do with how is the service duration determined, how is the arrival process determined, and also how is the buffer management done? Do we serve the first or the last or any other policy here? All of those are single server queue. Now let me apply Little's formula to just the server part of the queue. I break this queuing system into 2, a subsystem which is the buffer, possibly empty, and another system which is the server. And I apply Little's formula to the server only. Then what is the average response time in the server? Well, that's exactly what is called the service time. How much time, in average, a job spends being served. So that's what is classically called S. What is the average number of customers in this part of the queue? Well, the queue is either busy, there is one job in the queue because it's a single server queue, there can be only one job, or there is 0 job that happens when the buffer is empty and the last customer has left. So it can be 0 or 1. So the average is 0 times the probability that the queue is empty, plus 1, the probability that the server has 1, which is exactly occurring when the queue is non-empty. The queue is empty when the server is also empty here. So n is equal to the probability that the queue is non-empty. Therefore, we obtain this formula, which is called the utilization law. Lambda, the arrival rate, oh sorry, I should mention something. The arrival rate, if the system is stationary, the arrival rate out of the buffer is also the arrival into the buffer, is also the arrival rate out of the buffer. Otherwise, the queue will explode. So if the system is stationary, then the arrival rate into the server here is the arrival rate into the queue here. So we have this formula, arrival rate multiplied by service time is equal to the probability that the queue is non-empty, which can also be interpreted as the fraction of time that the queue is non-empty. So that is called the utilization law. In particular, probability is between 0 and 1. So we see that lambda times S should also always be less than 1. And this is called the utilization factor of the server. This is the proportion of time that the server is occupied, that it is busy. It should be less than 1 for this formula. If we can apply this formula, which is if this queue is stable, then the utilization should be less than 1, which is something that we had already discussed in the first week. In fact, it's an example of what we call a bottleneck analysis. We know that a server cannot be busy more than 100% of the time, and that gives us a first equation here. Very often, queuing systems involve multiple systems that are visited in some arbitrary order. Here is the first example that is a direct application of Little's formula. It's called the interactive user model. So this models a system where there are n users in total. So it's a closed system. You have circulating systems and circulating users, sorry. And the users arrive here. When they arrive, they get served. And when they are served, they go back to the pool here. So there is a finite number of users. There are up to n slots here. And one of the slots is empty when one of the users is in the service center. So let me apply Little's formula from point A to point B, right? So if the system is stable, and this system will be stable because it's closed, then the rate of circulation is the same at A here in the middle and at B. I call it lambda, which is the rate at which the service center receives transactions, multiplied by the response time. Now, what is the response time? Well, the response time is equal to the average time spent here in the buffer, plus the time spent in service here, which I call here R. It's the response time through the service center. Put a bar to say that those are the averages. Then the product of this, lambda times the total time, is equal to the average number of customers in the system. But since it's a closed system with n users, the number of customers is constant equal to n, so the average also. So that means that the average must be equal to n. So we have this quantity, this equation here, which has received a name. It's called the interactive user model. And it can be used, for example, to compute things like assume you're the manager of a car rental office in an airport. Of course, this is at a time where airports operate and people rent cars. So hopefully next fall. Then a software monitor has observed, for example, that the service center receives 5 transactions per second. So here a user is one of your employees who is sitting at their desk, hopefully working, but perhaps doing nothing or thinking in the best case here. So the software monitor monitors lambda, the arrival rate here, and also monitors the response time here to be 2 seconds here. There are 10 employees in total. What is the average think time? The think time, that's a terminology that's usually employed in this context, is the time you spend here. So this is a way of modeling how you use a computer or a web center. When you're in this mode here, you're thinking or reading or doing something, and then you send a request to the system. This request comes back to you, which causes you to think again. So what is the average think time that a manager could compute here? I close the poll in a second. We have 2 answers. Now it's numerical. It's a bit more complicated, but it's easy here. We apply the interactive user model. Lambda is the rate per second. We've seen there are 5 transactions per second. The average response time is 2. The total number of customers is 10. So we have this equation to solve, and that gives us 48 seconds. Voilà, so that's an example of how one quantity depends on the other. Again, it's an indirect consequence of Little's law. So Little's law is really the fundamental law in queuing systems that will give us a lot of simplifications. There is another law here, which is called the forced flow and total response, which are called the forced flows and total response laws, that are easy to understand. And if you think of a network as something similar to a network of fluid pipes, assume you have a network where you have jobs that arrive at the rate lambda. Then when a job arrives, it has to do a little trip through the network to visit a number of service centers a number of times. So it goes here, it goes there, etc. Perhaps probabilistic, of course, usually probabilistically, until the working is over and the job leaves the system. Then we have the first law that says that now if I zoom at one of the subcenters here, the average, the rate at which it receives jobs is equal to the rate at which jobs enter the network multiplied by VK, where VK is the average number of visits done by a customer to this node here. So if I instrument my tasks, my jobs here, and I count when a job arrives, how many times a job visits in its lifetime in the network this specific service center, I call it VK. And then if it visits in average 3.5 times this center, then the rate of arrival into this center is 3.5 times the rate of arrival into the network. And the second thing is, if I'm interested in the total response time, how much time one of those jobs was spent in the network here, then it will be given by this, the response time of a unit in this network multiplied by how many times in average I visit this unit, and I take the sum over all the units here, which is this formula. So those formulas are similar, well, they make sense, they are not rocket science, but they are, what is beautiful about them is that they are true like Little's formula. They're simpler than Little's formula, but they are true under the same conditions, either because you do a simulation and you count things right, or because you are in a stochastic process that is stable and has a stationary regime. Let's see an example. Here I'm giving an example of an interactive user model where here up to 4 users are sharing a network that has, for example, CPU and disk access. So this is an example, for example, modeling real-time systems, such as the controller of a car that goes, so there's a number of tasks that do their own thing here. And when a task arrives, it is queued in the CPU. And with some probability, that's all that happens. The task comes back to the CPU. But with some probability, it will go to a certain resource A, which is here a disk or a block of memory. Then do fetch some data, come back to the CPU, do the computation that results from fetching the data, go back to, and after that, perhaps go to another memory, perhaps or another disk. Perhaps one is a memory cache, the other is another cache, or a disk, and then return, etc. And do that forever. Here it's a closed system. Here. Then if we find that in average, we have those numbers here, so we know that a task, when it starts, will visit the CPU 102 times. We'll visit the block A 30 times, the block B 68 times. We know that the average response time in the CPU is that quantity at the block A and the block B, those quantities here. Then we can compute the average response time for a transaction by simply computing the formula that we saw before, adding everything here, 102 times the response time of the CPU, etc. That will give us the total response time. Which means that we can break the thing here that is global and hard to instrument into things that can be measured locally. That's an example of how this can be used. But another way this can be used is to perform a specific bottleneck analysis that's quite useful in order to do what I call first order analysis of queuing system. Second order analysis of queuing system gives us, for example, the distribution of response time. And this is what we need if we're interested, for example, in the tail latency in a data center, then we cannot simply do bottleneck analysis. But with bottleneck analysis, we will know when the tail latency is going to be large, and we will, as we will see, know already a lot of information about our system. So I will explain the method on this simple example that we saw a minute ago. And for example, assume the system is closed. It's, for example, as I said, an industrial, a real-time system, and we want to know what is the throughput, how many times per second a task is served by the CPU. And this is, of course, useful for dimensioning what kind of CPU we need, for example. The principles of bottleneck analysis are to apply all the deterministic laws that we have seen, the laws of physics, if you want, of the queuing systems. And so this is Little's formula, and use two observations, is that the waiting time is always non-negative, which another way to put it is that the response time at the system is equal to the waiting time plus the service time. And the waiting time is the variable part. That's the one you study with queuing theory. But if the system is very lightly utilized, the waiting time will be very small. So in the limit of zero utilization, it is zero. So when we use this bound here, we find bounds that are tight at low utilization. Another thing we will do is that any resource has a utilization factor that must be bounded by 1. We've seen the single server queue a minute ago. So the single server queue, we have the lambda times the service time must be less than 1. So that's an example of a law of this nature. And this will be close to 1 when the system is completely saturated. So at high utilization, this bound is tight. And that's the idea of bottleneck analysis. We find bounds that are true at the two ends of the spectrum. Therefore, if we have the two ends of the spectrum, that already tells us about this, a lot about the system, as we will see. So if we apply this to this system here, I apply Little's formula that we've seen before. So what do I need to know? I want to compute lambda, right? I'm saying if I have n jobs, n tasks that are using this system, how often will they generate traffic? And what is the rate of activity of my system? That's what I want to know. Sometimes we might be interested in other things, in particular Z or R, but here assume that's lambda I want to know. So I have this first relationship here, n times lambda Z bar plus R bar, or n is equal to lambda Z bar plus R bar. Then, which will give me this thing here, because we know the number of visits that a typical task does to the different places here. So this R bar, I replace it by this. So I have lambda is n over Z bar plus this here. I assume that R bar, Then, of course, R bar, RA, and RB, our CPU, RA, and RB, those are the response times. They depend on my queuing analysis, but I know that they are lower bounded by the service time, which here I assume to be independent of the load, which for real-time systems tends to be the case here, and is the case for non-real-time systems that are well-engineered, that don't go in congestion collapse. So the response time is equal to the service time plus queuing. So this is larger than or equal to that. It means that lambda, we obtain a lower bound, which is this. And this lower bound, we expect it to be accurate when the system is very lightly loaded, because n is small, or because the CPU is very fast, for example, and A and B are very fast, for example. So that's the first inequality we obtain. Second set of inequalities, the usage of the resources at CPU A and B must be bounded by 1. So what is the usage of a resource? It's the utilization factor, which is the lambda in multiplied by the average service time. This is the second law we saw. And the lambda in, by the forced flows law, is the number of visits multiplied by lambda. So we have this other 3 inequalities, which means that lambda is the minimum of those 3 things. If I put all of this together, I obtain those 2 bounds. So the first bound, number 1, gives me this straight line. If I plot on the x-axis n and on the y-axis the throughput, I obtain this bound here. And the second here gives us horizontal lines. Each of those quantities gives us one number. And the bottleneck gives us, in fact, the bounds. Here, the bottleneck is the CPU. So we obtain this line here. And we know that we are here when n is small, and we are there when n is large, at least with the assumptions that I made before, which is when there is no congestion collapse here. So what this will tell us is this black line. Of course, the red and the blue line, you will need a detailed analysis here, but we have already obtained a lot of information about the system. Voila, that's all we will see for today. Next week, we will continue the queuing theory part, and I will also invite you to do the quiz on queuing theory. For this week, I invite those of you who are not yet through with their quiz on the previous module on simulation to finish it. And I also wish you a lot of fun with the lab on queuing theory, on simulation, sorry. Goodbye now.